Sure.
Just start with the recording. So to the people who joined late, hello, and thank you for coming. Today we've got a very special guest to talk to us, namely Simon Weinberg. Currently, he's a project manager for the Quantum Satellite Program at the European Space Agency, but he's also worked on xenon thrusters and cryogenic coolers, amongst other things. He specializes in telecom, spacecraft systems engineering, magnetics, and electronics-related technologies for space, just to name a few things. So that everyone's aware, this talk will be recorded so you can watch it at a later date, but as some media on the slideshow we're about to see is marked as for limited distribution, the presentation itself cannot be recorded. So please everyone give him a warm welcome and let us begin. Over to you, Simon.
Thank you. Okay, so I thought what I do, I want to make sure that we have plenty of time to just talk. So what I thought I'd do is I kind of do a kind of backwards presentation. So I'm going to start by showing you a video, a commercial video, if you like, of my satellite and what it does, so that you get an idea of what it's all about. And then I'll take you through and show you a sort of pictorial history, just with photographs of how the satellite was made. And then after that, basically open up the floor for questions. Well, actually, you can ask questions while I'm showing you stuff. It's no problem at all. Yeah, maybe in sort of that section after I've been through the photographs and stuff, we can talk more about what I did for my career and how I got into ESA and what ESA does and all these kind of things. Okay, so it's we're starting kind of backwards, but I'm starting with the more sort of exciting, glamorous video. So I'm just going to share my screen here and cross fingers that I can find the right bit.
Yeah.
It like many good things, it comes from having the right technology available at the right time. So it's a kind of coincidence that certain technologies got developed, and then eventually it reached a point where somebody woke up one day and said, "Hey, we can do this, and we've never been able to do this before." Yeah. But the difficulty in doing it previously was partly to do with the weight, and it's always about weight on satellites. Yes. So it's partly to do with the weight of the equipment that you needed in order to do it, if you wanted to do it. So, for example, you need a computer, and you don't want to launch a massive, heavy computer. You needed a lot of sophisticated control equipment to translate the signals that you were getting. If you were doing something software defined on ground, you need to uplink that to the satellite, and then the satellite needs to interpret it, and then it needs to control the electronics on board to be able to do it. And the technology didn't exist for any of those things 5 years ago, or well, not 10 years ago, let's say. What we've had to do in order to make the leap to be able to do it is firstly to have a very, very high bandwidth on the uplink and the downlink, which is highly innovative and highly difficult to do, basically. Yeah. And to do that has required enormous amounts of electronics, and it's really I don't know how much you guys know about these kind of areas of engineering, but if you wanted a high bandwidth means that when you amplify a signal, you don't lose part of it, right? So yeah, if you play a piece of music and you put it through a narrow bandwidth filter, you'll only hear bits of it, like your equalizer on your music, hi-fi or whatever. So you'd only hear the bass, or you'd only hear the treble. And in order to amplify and hear everything perfectly, you need a very, very clean amplifying system. And that requires a lot of electronics, very sophisticated electronics, when you're talking about the sort of frequencies that we're talking about. So we're not talking about audio frequencies, we're talking about gigahertz frequencies. So, so that's 10 to the 9 per second. So bloody fast, basically. And so to be able to handle that through electronics and have the electronics which is sophisticated enough to do that without introducing loads of crap into the signal is the challenge. And that's where technology has sort of taken a while to develop. So high bandwidth is a key part of it.
Okay. Okay.
And the other thing is sort of figuring out on the broadcast side, figuring out how to combine. So when you broadcast on a satellite, you use tubes. Do any of you guys know what tubes are? Shout if you do. So you have, if you remember way back, if you've seen old-fashioned televisions before, not the ones we have now, which are flat screen, or old-fashioned computers with monitors. The monitors are like big, right? I mean, they're long.
Yeah.
Whereas nowadays we have something flat, and we use LEDs, for example. In the old days, you had a long monitor or a long, well, basically a long
screen.
And the reason for that is because you were broadcasting onto a screen from an emitter, which is called a tube. And tubes are also used in, you still see them in very high fidelity amplifiers for music. But basically they're vacuum tubes. So they're basically literally a tube of glass with a spinning magnetic field that goes around the in a cylinder shape. And the spinning magnetic field accelerates electrons, and it projects the electrons out, and they hit the screen of the TV. And that technology is what we use on satellites. So we have these big tubes. They're about this long. I'll show you some later, and they carry a certain amount of power, maybe 200-300 watts, and they emit at very, very high frequencies. And the technology to do that has developed from the 1930s up until probably the I mean, people are going to be offended if they could hear me saying this, but probably until about 1970 or something, the technology developed, and then after that, it's kind of plateaued. So we still invest a lot in that R&D, but we don't make much progress. So the efficiency of the tubes has plateaued at about 60%, and the size of the tube has plateaued, and so on. So all that development has actually not changed that much. But knowing how to so if you broadcast from one tube, you get one beam. But if you reflect, if you take a whole array of these tubes and you make them bounce off what we call a reflector, which is a carbon fiber antenna, then because of the frequencies that they're working on, they literally do bounce like on a mirror, and you can combine them together. When they bounce, you can combine the beams from the different tubes together into the sort of shapes that we saw broadcast onto the Earth. You saw all those different and the technology of how to do that is very sophisticated as well, and that's also one of the things that's developed.
Are those reflectors? Are those are installed on Earth? And when you produce a beam, is the beam produced going on a reflector on Earth and going back to another satellite to like magnify the signal, or is it just transferred from the reflector? Where are the reflectors?
When you broadcast on Earth, you maybe you saw those patterns. You can, for example, if you watch Sky TV, they run satellites which have on them a British Isles shaped antenna.
Okay.
And because they only have a license to broadcast over the British Isles, so they broadcast down, and that pattern arrives on Earth with a certain density, what they call a power density. And anybody who puts a satellite dish up, of the sort of size that we're talking about, will get a certain amount of effective power onto that antenna, which it then collects, and then that goes through a load of amplifiers and comes out on your telly. Basically.
Okay.
So a reflector is just another name for an antenna, but we call it reflector.
Okay. It just takes wider area of signal.
Normally an antenna is designed to absorb the signal, but the reflector is designed to reflect the signal.
Okay.
That's basically what it is. Okay.
Thanks.
That was lesson number 1 of many. So I thought, is any more questions on the video, or should we move on to the pictures? Is that okay?
Yeah.
Okay, so then I'll share back the photographs.
Are there any plans, for example, in ESA's, like in ESA plans to launch?
We call it ESA.
ESA. Sorry, ESA has plans to launch with private companies, like private launch companies, or is it always going to be dependent on the just European Union, European unions? Like
we at ESA, we started the Ariane company. It's a commercial company, but we still have very much our fingers in Ariane, because it's considered politically correct, politically appropriate to have a European-based launcher. We don't want to rely on other countries. So ESA, so when you launch, you're encouraged to launch with ESA. You don't have to, and we sometimes don't, but we're encouraged to launch with Ariane so that we support a European industry rather than supporting a Russian industry or an American industry, for example.
Okay.
I've got a question actually. So how is it that you actually managed to transport the satellite from France or the UK to French Guiana? Because I'd imagine that, you know, it'd be quite fragile. You know, there's lots of very delicate parts. So how is it that you actually get it safely, you know?
Yeah. When it's ready to be packed away, it looks a bit like that picture I just showed you, and then it's shoved into a box with a lot of padding and a lot of precautions, and the box is custom made by a specialist, so that it fits around the satellite perfectly. And then we put in shock sensors to make sure that we have some traceability if something goes wrong. So if somebody drops the box and doesn't tell us about it, we'll know, because there's sensors on board inside the box. And then it's actually shipped out of Toulouse in France, and Airbus, that's where Airbus make their aeroplanes. So there's a big airport with a huge runway, and we take it by lorry to that airport, and then it's then dropped off on a plane. Now there's only, for most of these big satellites like mine, there's only one plane in the world which can be used to transport the satellite, because it has to be very large, and that's a Russian Illusion, and they are only available from Russia or from Ukraine, and so we have to book one of those, and it's just gigantic, and then it has at the back of the plane, it opens up. You have this huge opening, and then basically you shunt it from the lorry into the plane, and then it flies off to French Guiana. And then we always have somebody on board the plane to make sure there's no funny business. And then we have people who receive it in Cayenne, which is the capital of French Guiana. The airport.
Is Airbus not using Beluga plane? Is it not big enough?
I don't know, but I guess by definition it isn't, because they're not using it. But is Beluga a transport plane?
I think so. Well, like you know, the whale-sized, like whale-shaped plane, that big one.
Yeah. Oh, you mean the what's it called? Anyway, no, I think that one, they don't make them in a transport or form. I mean, remember, this is very niche. You know, there isn't room on the market for lots and lots of planes with different competing for each other for the transports. You know, because there isn't that many transports. So
okay.
So
but still, Airbus is the final assembler, right, of the satellite. Is the final assembly done in the Airbus plant? Is it, and then
it's not the same Airbus as the people who make the planes. It's
it's space sector.
Yeah, I mean, we're much more demanding, you know, because of the clean rooms and the the components we're using and so on. We're much more demanding than the plane manufacturer, which would be much more commercialized. We're much more kind of artisanal in a way. You know, every satellite's different.
Okay. And
so if it's okay with you, then I was going to open just for questions, and what I haven't really covered is my own career and how I got into ESA. And I know you were, at least Archie was saying, you'd be interested in that. So I don't know if you want to ask questions, or I can talk about it.
Yeah, I just want to know, how did you got involved with ESA? You were I think, did you work on Eutelsat before? I think I've seen on your profile as well, like you had experience before ESA with satellites.
I did, yeah.
Yeah. Okay.
No, so so if I wind back the clock a bit, so I did physics and applied physics at Nottingham, and I liked the applied physics, and it was called With Electronics, and so we had to do some electronics projects, and I really enjoyed them. That was my kind of the thing that I was attracted to most. So I decided to do a master's degree rather than get a job straight away. So I did a MSc at Loughborough University in electronics, and the field of electronics is power electronics.
Yeah.
That was more about things like generating stations, power turbines, all this kind of stuff that actually I wasn't that interested in, but I was just interested in the electronics side. Yeah. But we did have one course which was on power converters, which are the things that take energy, take, for example, the voltage of a battery in your car and turn it into the right voltage to use elsewhere in the car. And or on a satellite, they take the power from the solar ray and somehow turn that into a steady voltage, which is used to supply all the electronics on board. So it was that kind of thing. So they're everywhere. Power converters are everywhere. So I got interested in that, and I did my master's degree project. I built an uninterruptible power supply as my master's degree project, and the supervisor liked me and liked what I did and said, "Would you want to stay and do a PhD?" And I was a bit dubious because I thought, well, PhD is very theoretical, whatever. Yeah. But he said, no, we've got a company that is interested in developing a very state-of-the-art power supply, much smaller than any others that are being made. And they're looking for a competitive edge. And, you'd be working with them and it would be really making a product. So I said, okay. So I did a PhD for 3 years, also at Loughborough. Yeah. And then when I finished that, I was looking around for a job in that field, and I applied for loads of different jobs. But there was basically one company that really attracted me, which was a company in Belgium. It's now called Alcatel. Actually, no, it's now called Thales, but it was called something else at the time, and it was deep in the south of Belgium. I was kind of interested in going abroad because I'd grown up here in Holland anyway, even though I'm British. And I went for an interview there, and I was just blown away by all the equipment they had in the lab. So I accepted a job offer from them. It wasn't the best job offer I got, but it was, I really was attracted to them. And so I started work there, and I worked in Belgium for 4 years. And I was brought on as a kind of specialist in this area of electronics that I'd been working on for my PhD. So that was a great head start for me career-wise. And basically they were only doing equipment for space. And I moved, so I worked with them for 4 years. Then I moved, I fancied a change. So I moved to a company in Spain that were also doing electronics for space. And I got a bit of a promotion and blah, blah, blah. So I worked in just outside Madrid for almost 4 years. And then actually then I had a little baby girl. So we decided that we would like to maybe go back to the UK. So we moved back to the UK, and that's when I had this bizarre experience working in Airbus, what's now Airbus in Stevenage, where they actually employed me to be a specialist in electronics, but then they didn't have any work for me. So after about 6 months of twiddling my thumbs, I started to get involved in loads of other stuff. And I've always been a very curious person. So, I was always interested in loads of different subjects. And they through various sort of coincidences and stuff, I ended up working on all these different things. So as Archie mentioned at the beginning, I was a project manager for cryogenic coolers, which are used in science spacecraft. So there's one called Herschel Planck that you may have heard of.
Oh yeah, yeah.
I mean, the idea there is that they have to cool all their instruments down because they're pointing at stars, I guess. Yeah. And they're getting a lot of heat. So cryogenic coolers, the Herschel Planck one had to go down to 4 degrees Kelvin. And it was a very, very tiny detector on the end of a very large telescope. And at the very end, you had this tiny little detector, and you had to cool that tiny little detector down to 4 degrees Kelvin so that you could actually get it to work optimally. So I worked on various cryogenic coolers, but what we were doing was actually making the coolers themselves, but very, very challenging. I worked on another project called Integral, which is also a science spacecraft. So I did that for a while. And then I also got involved in electric propulsion. So electric propulsion, I told you all about the gas that's coming out, and I told you about the rocket engines and all that. Well, that's not electric propulsion. Electric propulsion is using a thing that's almost like one of those tubes I described to you before.
Yeah.
And what they do is they cut the end off the tube, and then they pump xenon into the tube, and then they ionize the xenon as it moves through the tube on these magnetic fields that I was describing earlier. And as they ionize it, it turns into xenon's quite a big atom, and they ionize, or a big ion, they ionize these ions, and the ions get projected out of the spacecraft, and that gives you propulsion. And when you see Star Trek or anything like that, you see anything science fiction-y, they always have a blue sort of kind of flare coming out of the back of the propulsion system. Well, that's xenon, because that's the color xenon makes when it's ionized. It's very, very pretty. But I worked on these ion propulsion engines, which was partly all about high voltage electronics and partly about the physics of the thrusters themselves. So I did that, and then I also worked on the power supplies that you use for these tubes. So I had some interesting experiences doing that. So basically, I did a whole bunch of stuff. I had 5 different jobs in 2.5 years when I worked there. And then after that, I kind of gave up, and I got offered a job at Eutelsat in Paris. And that's where I moved, and I worked for Eutelsat for a few years, which is manic, but good fun. And then I actually, I mean, this is very unusual, actually, it seems, but I actually just sent my CV into ESA and said, "Is there any jobs?" And because I had a very wide experience, they were very interested, so they offered me a job, and they created a vacancy for me. But normally it doesn't work like that. Normally, what happens is they have a website and they put a vacancy note out, and you apply it with everybody else, and you show your CV and you get an interview, whatever. But that's how I got into ESA, and I must say, when I got into ESA, I mean, ESA is the pinnacle of space in Europe, in the sense that, you know, I was working for all these different industries, but our customer was almost always ESA, you know. And when you get to ESA, you then become the customer. So you could get to use all your experience that you've learned to sort of work together with people like you, who are still working in industry. And you have a lot of, let's say, a lot of control. You have a lot of you have a lot of power, if you want to have a lot of power, which some people enjoy. And but to me, what's interesting is you also have the ability to come up with ideas and say, "Hey, let's put out a contract and see who can make one of these." And that's basically what I did for the first 4 years that I was in ESA. Was I just came up with ideas, and then I ran projects with companies across Europe, because ESA's role is basically we have 2 roles really. One is to be the technical expert. So they try to keep it that we know more than everybody else, because we have to help them. We have to help everybody across Europe to do the best that they can to further the technology and so on. And the other role we have is that we get money from government. So we get 4 billion euros budget every 3 years, more or less, or 4 or 5, and we spend that money. We don't keep it for ourselves. We spend that money on industry, and it's almost like we give grants. But part of our mandate is to not just write a check and hand it over, but also to supervise the people that are spending the money and make sure that they're doing it properly, and to guide them. So we're a kind of authority in that sense. So we have lots of roles, and as far as astronomy goes, we also have a bunch of scientists who are, like I said, coming up with ideas, they're coming up with ideas. Well, what's the next satellite going to do? What, after we've been to Mars, what do we do next? Or, after we launch James Webb, what's the next thing we want to look at? What's the next comet we want to land on? All this kind of stuff. So we have astronomers, and we have other scientists which are working on that, but they're also dealing with everybody in all the different countries across Europe who all want something, right? So can we do an experiment on microbiology? For example, can we have a microbiology experiment on the International Space Station? Well, yeah, okay. How many people want to do that? Okay, what kind of experiment are we going to do?
Yeah.
And we create these. We funnel it up until it gets to ESA, and then eventually we have to convince governments to fund it, and then once we got the funding, then we manage it basically.
Yeah.
So,
also, you mentioned ion thrusters. I was thinking, is there any use in satellite industry for ion thrusters? Could it replace, for example, current standard propulsion system?
Yeah, no. Sorry, maybe I didn't explain it very well, but that's what I was doing. I was making ion thrusters for satellites. Yeah.
Okay.
So satellites have become more and more are using more and more ion thrusters because.
Yeah.
For example, one example of how to use them would be that instead of launching in the geostationary orbit, like I am for quantum, you launch in a lower orbit, and then you run an electric propulsion motor, which doesn't use that much gas, and then you push the satellite up into the higher orbit, and that takes about 6 months.
But it's possible.
It saves you, but it is possible, and it saves you a lot of money because you don't have to launch so high. So the launch costs are much lower.
Is the way that ion propulsion works, is it like to do with like you've got a chamber full of like negative ions and there's a bit of an opening and then they all want to get away from each other, and that's kind of how it works? Like they all
it's like you have a kind of accelerator formed by magnetic coils. So you have an electromagnet which is created using a power supply, and that has a directional polarity, if you like, so that what you do is you start with xenon, and then the xenon is ionized by the magnetic field because it's so high voltage, but then it's also encouraged to move because once it has a polarity, it's encouraged to move towards the. So you have a, just like in a battery, for example, you have an anode and a cathode. So you polarize it at the anode, and you have a cathode at the other end, and there's the xenon ions are attracted towards the cathode, but because you have a hole, basically they go, whoops, that's a bit too fast, and we missed it, boom, and off they go, and they're outside the spacecraft, and then you have a grid across the end which is repelling them, so it stops them coming back again. So it keeps them moving out.
Oh, right. Okay,
yeah. So it's really cool, actually. It's really incredibly cool. And we have a test chamber here in ESA where you can see them testing them. And I can tell you, I was heavily involved in that stuff for a while. Also, when I got to ESA, I also ran some contracts making an ion thruster in the UK. But yeah, they're pretty impressive, and they're very, very efficient in terms of how much gas you need
to
make them work. So yeah. So that was a bit about my career and how I got there. I mean, I went pretty fast, but if you let's say one day you were interested in working for ESA, I think there's two ways of doing that. The first one is to get loads of experience like I did and sort of work your way through different space industries and then eventually apply. And the other way which is in a way more interesting, is to apply for the young graduate trainee scheme. And that opens every year. I can't remember when, but you can find it on the ESA website. And basically that we take literally people who've just graduated from university and pay them quite a bit of money and stick them in different parts of the organization. And then I've actually had several YGTs in my team, and it's great. I mean, because we get to use them a little bit like slave labor. You know, give them all the tasks that are, you know, that are maybe good for beginners, if you like, and they get to sort of play around with all kinds of different stuff.
Yeah.
So it's a real win-win. And in fact, one of my members of my team now is an Italian lady who started off as a YGT, young graduate trainee, and she was so good that we extended her contract. Normally it's 1 year. We extended her contract for another year, and then after that we employed her. So she's come straight into the job. But that's quite unusual. But it's a great opportunity. You can, as I say, the salary is good. You get free training. What's not to like, you know? So you'll see every year the different areas of ESA advertised for trainees, and you may not always get ones in the area that you want. Of course, that's the thing, and there is a lot of competition. So, you know, if you want to go for something like that, if you've done summer jobs or you've got some kind of work experience, that always helps on your CV. If you know about ESA and you know what we do, you will definitely get asked that at the interview, you know. So you have to show that you've really taken an interest in and you have an understanding of what we do. You can watch this video again. Yeah, but yeah, that's an interesting opportunity. So.
Yeah, that's definitely one to look for. I've seen it before, and like the only thing I need right now is the degree. Like I need to graduate first, but yeah.
Exactly.
It's really
and just to say also that ESA is we have branches all over. So I mentioned in the UK there's one now. There's also the big technical one is here in Holland. That's called ESTEC. And then we have a headquarters in Paris, which is more admin. And we have a center in Italy, which is, I guess, a mixture. And then we have in Spain, we have a center which is more to do with receiving and well, it's telescopes and antennas basically pointing into the sky. So it's a lot of work to do with that, receiving signals, controlling satellites, looking at the universe basically. But it's in the middle of nowhere in the Spanish desert, if you like. So it's isolated from light and so on. Yeah, so there's a number of different places that you can work. So yeah. Have I worn you all out?
I think this was initially supposed to be about an hour long.
No, definitely the content is great. I just love it.
I think you're well prepared for your BBC interview now, Simon.
Maybe. So is there any other questions? Anything, you know, just you can ask me anything. I may not be able to answer it, but you can ask me anything you like.
So the satellite itself is called Quantum, and it can obviously do like new things that's never been done before. Does it make special use of quantum theory? Is that why it can do these things?
Okay, unfortunately not.
Oh, disappointing.
Because you know, I'm sure you guys know that there's a lot of geeky people involved in anything to do with engineering, and when quantum was first conceived as a project, some wise spark decided to call it AnySat, and the problem working in ESA, one of the nice things about working in ESA is it's so international, but whoever thought of AnySat as a name for a satellite, you know, wasn't a great British language speaker, let's say, because AnySat just said, oh, it's any old sat, you know. So it was a horrible name. And then Eutelsat, who were going to commercialize the satellite, came up with this name Quantum because they thought it sounded fancy. But it's nothing to do with quantum theory. And the funny thing is that we now do have a satellite that we're working on, which is to do with quantum theory. And it's called QKD, Quantum Key Distribution. And it's, yeah, I'm incredibly ignorant about it, but it does sound very, very interesting, you know, because the whole quantum theory stuff, it seems that nobody really understands it. They just know it happens and it works. And, you know, so I think the Chinese are actually the ahead of us, because they already have the quantum-based satellite, but we are hoping to get ours up in the next few years, and
Yeah,
I think it'll be really interesting, actually.
yeah, that's really cool how we sort of maybe understand it, but we use it anyway, like before we
Exactly. Yeah, it's crazy. It's absolutely crazy. So yeah. So no, it's just I mean, I think quantum, I think we signed the contract soon after Quantum of Solace was made as a film, so maybe that's where they got the idea from.
Just sounds cool. It just looks good.
Yeah, exactly. Just sounds good. Yeah, I mean, the commercial satellite business is quite interesting. It's not it's not like anything else that ESA does, because most of the stuff that we do is completely not for profit. I mean, it's about, you know, sending something to Mars or up to look at stars and so on. It's really nothing to do with money. It's all to do with science. Yeah. But the telecommunications satellites that we support, it's all about trying to get or keep Europe as a good competitor. And there's an enormous amount of jobs associated with it, and money associated with it. And so we always have to think about how much everything costs, you know, and that's very different. And that's I like that, and that's kind of the same reason why I preferred applied physics to pure physics. It's kind of, to me, it's more hands-on. So I quite enjoy that challenge of the commercialization of space. And Eutelsat, you know, they're contributing towards the cost of the satellite, and we are contributing towards the cost of the research and development elements of the satellite. But Eutelsat will launch it, and once they've launched it, which is hopefully going to be in July, but we're still waiting because Ariane has an issue with the launcher. So we were actually supposed to launch last year, and it's been delayed while we wait for Ariane to sort the problem out. But when it does get launched, then they will have customers jumping on it, and they will start to make money from it, and you get your money back quite quickly on the satellite, actually. But you know, the sort of costs we're talking about for us, this kind of satellite is of the order of anywhere between 250 and 500 million.
Wow.
Yeah. Yeah.
I went to a talk, it was a few years ago now, from Matt Taylor about the Rosetta mission. And it was like a great talk, and then at the end it was like, so what now? And it was like, well, we ran out of funding. So it's like, it was quite sad, to be honest. There's just like a satellite just sitting on a comet somewhere.
Yeah.
Hopefully that doesn't happen.
Is that what you said? They run out of funding? Wow.
Yeah, he said that they ran out of funding.
Because I would have thought they also have problems to access the whatever data they left, isn't it? But yeah, Rosetta was an amazing project.
Yeah, it was. I remember it all over the news.
Yeah.
At the time.
And it started so long ago. I mean, it took years and years to get it to the right place. And
yeah,
he
said it was like riding a horse blindfolded while trying to shoot a gun towards a coin that had been thrown up in the air to get he said it was literally so technically difficult, but
isn't it
impossible, but it wasn't.
Isn't it on that one that they actually originally were aiming for a different comet?
I can't remember. I just remember it being duck shaped, and it was like they nicknamed it Chewy Gooey because it was called like Churyumov Gerasimenko or something. So it was like too much of a mouthful. But yeah, I remember that. It was really exciting. But yeah, it was like a bit of a like at the end.
Yeah.
With it now, not getting any money.
But I guess they got what they wanted from it.
Yeah, definitely.
It's a pretty amazing project, actually.
Yeah, it was.
Yeah, they had. I think it was that one where they had issues with the. I think it was with the launcher or something. I can't remember now. But they missed the launch slot originally for the first. Because it's often, well, you guys know more about this than me. So, for example, I mean, if we want to go to Mars, there's certain windows where we can launch and get to Mars more easily because of gravitational pull and doing what are they called? Loops around, what's he called?
Slingshotting?
Yeah, slingshotting, exactly. Doing slingshots. And if you miss that, if you miss your window because your project's late, oops, well, there's not another window for 3 years, or so you have to wait 3 years for the next one. So it's where project management becomes quite challenging, actually, to make sure you do everything on time. And I didn't really go into it, but I mean, a project like Quantum, there's so much innovation on there. There's so many unknowns when you start the project. You just don't know. You just have to handle things as they come along and try and fix them and try and keep the schedule what it was supposed to be and so on. It's actually, it's basically an R&D project that you're doing in the middle of while having a commitment at the end that you have to launch. So for us, it's a real shame because we should have launched last year and we were actually on time, and then the blooming rocket doesn't work anymore. So we actually have to hang around, and that's kind of a bit sad because we put everything on, we did everything we could to try and keep the schedule. So, but that's the way it is. Such is life. So I don't know, are there more questions? Do we want to wrap up? Up to you.
I think if there aren't any more questions, I'd just like to say that thank you for taking time out of your day to make that slideshow, which is very interesting. And I think everyone here should feel quite special that they've been able to see the rocket that the satellite will be in. Very first people.
We got exclusive information.
Yeah,
we got exclusive photos.
Yeah. Oh, well, it was my pleasure, Archie, and thanks for asking me. And for me, the motivation is really just to get people interested and to understand, get people to understand what it's all about. And if any of you, and I do mean this most sincerely, if any of you want to get in touch after this, Archie's got my email.
Mm-hmm.
You can send it round, Archie. I really don't mind. And if people want to ask me any questions, or in the future maybe I can help with something, just let me know. So it's always good to help. So
that's great to know. I'll
Great.
Yeah.
It was definitely good learning, like a lecture about satellites. I never heard so much about satellites from
and what we talked about was literally the very tip of the iceberg. I mean, there's so much more to every element of it. It's really, there's of course an awful lot of heritage that goes into these things, the knowledge that's been built up over years and years and years. Just like the first time they launched satellites, they didn't put any of that foil around the outside, and they all went wrong, and everybody scratched their heads and went, "Ooh, what did we do wrong? What can we do?" It's such a learning experience and I've actually seen some of the old documents from the 1970s, and it's really interesting to see some of the stuff that they were doing then. But we're also pioneering. I mean, but where we're pioneering is in the functionality of the satellite and the electronics behind it, which is, as I said many times, is very complicated. Okay.
Thank you.
Well,
thank you. Thank you very much.
Thank you very much.
Thanks for your time.
It's a pleasure. Take care.
It was amazing to have you here. Have a nice evening.
Thank you. You too.
You too.
Bye.
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 You.
Bye.